Hello. Let's implement principal component analysis with Python. So now I actually copied some code. So this part is to import a module about Google, to use Google Drive. Basically, I want import data from Google spreadsheet. Okay, and this is for authentication. And here I import the NumPy, Pandas, Tablet, Seaborn, and test model, and sklearn, decomposition PCA. This is the important part, and the Matplotlib library. And here, sheet 1 is from this address, this address for Google spreadsheet, open by key, and then I read one, and the daily return tab, okay, from the sheet. Actually, in the spreadsheet there are many sheets, and then one of the sheet I input the data, and it is temp one, and read this one as a data frame, and then read the data as a daily return. So it is daily return, and then the daily return here. Okay, let me print daily return health. Okay, and run it. So, well, it takes some time to import the data. So data looks like this. So the very first column is, as you can see, the very first column is the date. So date starts from 2015. And they are basically tickers for Korean stocks. And they are daily returns. Okay. And then what I do here is that I set index. I regard this as not a column information. I regard this one as the index. And then read print again. Then what we can see is, well, what I do is basically then now it is tail. So this one, right? So this very first date here, now it becomes index. Date becomes index. So first column is the first asset, and then we have assets. So basically we have 500, no, we have 820 stock return data. Okay, so dimension of the data, 820 number of stocks. And then the length of data is data starts from 2015 to 2020. So it is like 6 years, 5 years of the data. We have 5 years data for 5 years of stock return data for 820 stocks. And 820 stocks, there are too many. Too many to manage. So basically we want to reduce the dimension of the 820 stocks into several orthogonal portfolios. We reduce 820 into several smaller number of portfolio, which we call principal component. Okay. So what are we going to do? So what we can do first is then, well, actually, so, and then what we can do is another one is basically Fama-Frenchy three factors. In finance, we have very important concept for Fama-Frenchy three factors, and then we import the Fama-Frenchy three factor data over here. So where the index is again date, and then the first column of Fama-Frenchy three factors is market factor. Second one is SMB, is called size factor. Third one, HML, is called like value factor, and last one is basically risk-free rate. Okay, and then we have to normalize the data, right? So daily return. Okay, daily return, but rest name is 2 equal. As you know, in the principal component analysis, we shift data to the mean. So we want to make mean 0, data mean 0, right? So what we are gonna do is like a daily return, and then minus we shift to mean, right? So basically we wanna do is daily return and then mean like this one, okay? Then we are demeaned basically, okay? And then so let's daily RTN2 mean should be 0, right? So they are very close to 0 or close to 0. But in the, it is like a daily stock return. So daily stock return, we expect daily stock return are in expectation. It is close to 0 anyway. So, well, it is optional, but I usually skip this one. So actually, when I analyze stock return data, I don't usually adjust mean because, well, first, daily stock return, mean of the daily stock return is very close to 0. Second, well, the mean of the stock return is very, very, very difficult to estimate, right? If we know what is going to happen tomorrow, right? If we know what is going to happen to stock return, then we can make a lot of money, right? So it is no wonder that it is very hard to estimate the stock return. So it is intuitively should be closer to 0. So that if it is negative, we can short sell. If it is positive, we can buy. So it should be intuitively close to 0. So that it is difficult to make money, right? So therefore, I do usually don't normalize it. So if I don't normalize it, then, well, it is not exactly 0, but it is still very close to 0, right? Anyway, so yeah, I skip this part. Okay, so normalize. So here we are shift mean of the mean to 0, but for stock returns, it is optional because of the because of the efficient market hypothesis, which means that basically efficient market hypothesis means that it is very hard to make money, which means that it is very hard to predict stock return with a simple analysis. Okay, and then let's check daily return 2, and then we can check information about that. Information is pandas frame, and then length of data. We have like 5 years of data, so we have 1,373 entries, and then we have 820 entries for columns. So we have 820. We have 820 stock names, right? And then it's for float. And the next, well, we can also check pharma French 3 factors. So here, pharma French 3 factors, the information. Well, if we check information, again, I match the rank. So we have 1,373 entries. We have actually matched date, and they are column names, market returns, market factors, even pharma French, one of the pharma French factors, and then this is size factor, value factor, high minus low, and this risk-free rate. Good. So everything seems fine. So data looks okay. And then we can do PCA, and then we can do PCA PCA, let's to save, okay, to save notation. Okay, I call PCA into the small PCA, cat PCA, and then we can fit the data. We can do PCA and the fit of the data. Our data is one daily RTN2, which is possibly normalized. And we fit the data, then yeah, and components none. So I think it is done well. Okay. And then what we can check is what we can check is first let's check eigenvalue and eigenvectors. Eigenvalue is again, eigenvalue is roughly you can regard that as the like variance of the principal component. Variance of first principal component. Okay. So first eigenvalue should be biggest by definition of PCA. So let's calculate eigenvalue, and eigenvector, eigenvalue and eigenvector. And eigenvalue and eigenvector is eigenvalue is like variance. So PCA and explained variance. Okay, explained variance. And the eigenvector is PCA, and then PCA, and then it is a component, right? It is a components, PCA component. And then let's transpose this to see it easily, transpose, okay? And then eigenvalue, okay? So we have this 800 because we have 820 SS, so we have 820 eigenvalues, but the first one is the greatest, the second one is smallest. So, well, we can cut eigenvalue somewhere so that we can keep only largest eigenvalue to reduce dimension. Okay, let's check eigenvalue, eigenvector. Eigenvector is, yeah, it is a big matrix. So, well, it should be still big. So, yeah. Wow, this takes some time. And then, yeah, exceeded. Yeah, so anyway, so, and then I want to give names in the data. So, well, I want to leave the names of the data. So PC columns, I want to give column names of the principal component. So in order to give column names, I do PC, right? And then string. I add string I, okay? String I. They are names for the principal component, And then for I in, so range, let's, in Python, the first element is 0, right? So, but I want to make 1. And then we have 820, so the rest one is 821. Okay. Sorry, so we have 821 number of stocks, right? So let's check the name, PC columns. Okay, so I have names for principal components. They are fine. I have good names. And then eigenvector. I can assign the name to eigenvector. So I will do eigenvector. Eigenvector is basically data frame, PD data frame. And then input data is again eigenvector. eigenvector. And then index is the name for row. Index should be same to our original data, RTN. I thought RTN daily. RTN daily. I think daily. No, the name was like daily. Yeah, daily RTN. Okay, and I use this index, right? Index is name of this index. Columns, and then, well, the column name is I define the names of this one. Okay, so, well, again, to remind you, what I'm doing is that eigenvector is basically, well, to remind you, what we do is that we are basically reduce dimension. This is the original data. So we have 821, right? And then we have length is like 1000, like something, right? And then by multiplying, we have some number of principal components, so that, well, here, because theoretically we can select 821. Actually, to reduce dimension, we reduce this one like 10, something like this one. But because we have this number of data, still we have 821 number of principal component, but we will not use everything. We will use like a couple of things. But here, therefore, this one in the linear algebra, this one is in line of this one, which is basically this part, and this one. This is the name of the principal component over here. Name. Okay, that's what I did. Okay. Okay, good. So I give names or eigenvectors. Okay, and then, well, then principal component is, as you can see. Okay, I shouldn't have deleted that, but as you, again, the principal component analysis, this is the original data. This original data is like daily RTN2, right? And then this is eigenvector, E vector, eigenvector. And then this will generate this PC principal, this will generate this principal component over here. They are like PC principal component. Okay, and then this is the length of data T, and then this is T, 820. And then by now we select everything, but we reduce data, but reduce dimension. So if it becomes 10, we will becomes like a PCA 1 to PCA 10. That's something what I do. So we have to generate this principal component. Okay. We will generate this principal component. So what we have to do is we have to multiply this original data and eigenvector. Okay, and let's do that. So let's multiply PC principal component is daily return to, and then matrix algebra and eigenvector. Okay, then we get principal component, and then let's print PC head. Okay, so we have, so they are orthogonal to each other. Okay, so we did principal component each other. So this explains most variation, and its variance is normalized to 1, and that they are all orthogonal to each other. But its eigenvalue is biggest. PC1's eigenvalue is biggest, and its eigenvalue is roughly it is actually variance of the first the largest variation. Okay, that's the variation to the direction of PC1. Okay, so far so good. And then we can check something. So again, eigenvectors are like this principal component are orthogonal to each other. So let's actually check it whether they are orthogonal to each other. So what we can do is actually eigenvector. Okay, and then what we can do is okay, PC. Oh, actually, yeah. Well, I have to. Yeah, I have to. Yes. So actually, so the principal component, the first one principal component, the first one is like this one. Their correlation. Oh, they are not exactly orthogonal, but yeah, that's fine. But instead, let's check the uh, relation between eigenvectors. So print eigenvector, and then there is always a numerical regular. So multiply eigenvector. Okay, at least they are quite well normalized. Each vector, the weight vector in Wikipedia. Do you remember the weight vector? Weight vectors are orthogonal to each other, and then where ranks of the weight vector is 1. So yeah, variance is 1, and then they are all practically 0. So they are fine. To tabulate this one, well, tabulation, let me see. It is maybe simply too large for tabulation, but let's see. Maybe too large. Yeah, too large. Okay, so yeah, again, we can check this one and then print, and then we can go to next code, and then, well, let's check the diagonal term of this one, MP diagonal term of this one, and they are should be all ones, right? Exactly, they are 1, 821 number of ones. Good, good. And then what we can do is the next, as I told you, the variance of the principal component. So principal component looks like this. So variance of this one. I told you variance of the principal components are like this one. They should be same to eigenvalue, right? They should be same to eigenvalue. So let's check this one with eigenvalue. So, well, I want to check this one with eigenvalue, and they should be exactly same. Variance of the principal component is same to eigenvalue. So I want to zip it to see together, and then to make a list, and then to make tabulate, and then to print. And then, yeah, they are exactly same. Yeah, they are all same, right? Yeah, they are, yeah, all same, exactly same, right? So eigenvalues are exactly the variance of each principal component. Good. They are simply too many, so let's list tabulate this one, and then 0 to 5. Let's take a look at from 0 to 5. And then, yeah, they are exactly the same. Actually, I don't have to type 0, so yeah, good. So they are exactly the same, okay? Okay, and then let's check the graph. So let's check the size of the let's check the size of the eigenvalue. So to generate graph, what I can do is Seaborn, okay, Seaborn, and then PLT figure, and the PLT show. I want to show the figure, and then, well, let me see the grid, PLT grid. True. Okay, so we have grid. I want to see the pattern of the eigenvalue over here, and then and then plot, and then PC dot explained PC dot x PCA actually PCA dot explained variance. Okay, so well, it drops dramatically. So well, it is not y to everything. So let's see, just up to 10. Yeah, up to 10 looks like this. The first principal component very large. And then why don't we look at the from second one? From second one is again very large. Okay, from 0 looks like this. And then marker is, let's check. Okay, that's so well. It's, yeah, D. Yeah, diamond is better. Yes, so looks like this. So yeah, when we reduce dimension, if we use all 821, principal components, then there is no dimension reduction. So we have to select the reduced dimension, size of the reduced dimension, and there is like more of the arts and science. So what usually people do is that, let's see 100. At some point, principal component drops significantly. So in this case, maybe it dropped significantly. Around at this point. So maybe we select just the four first principal components, which means then we have like 821 number of stock into 4 number of portfolio. Okay. Actually, if it is too dramatic, what we can do is actually let's make it 20. Let's make it 20. Yeah, 20, then yeah, it is reasonable. So yeah, it is hard to tell, but clearly, if I am do the analysis, I think I'll cut the point somewhere here or here. select the 3 principal component or 4 principal component, which is actually in line with the intuition of the Fama French. Fama French suggested like a 3-factor model or 5-factor model. 5-factor model means 1, 2, 3, 4, 5, or select over here. Let's check whether 5-factor model works. So let's check. If we start from first one, it is too large. From let's start third one to 20. So third, yeah, fourth, 5, yes. So if we select over here, it is like Fama French 5-factor model. Okay. Yeah. So maybe we can cut over here and then remove all principal components at this point. And then what we can do is, yes, right? That's what we can do. And then our original data, is like this PC principal component, right? PC. So print PC head. Okay. So yeah, if select everything, it looks like this one. But if we select just the first 5 principal component, then what we does is, right? Huh. Actually, it is always confusing. Oh, always confusing. That's in that way, yeah. Yes, actually, this is. So if we choose the first 5 principal components, then PC1, I think I have to type where this is. PC2, yeah, PC1 and PC2, like this one, okay. Then I select the first principal component. So I basically reduce dimension from like 821 stack to 2 dimension, right? But as you can see again, since the eigenvalue drop suddenly around this point, then actually drop significantly around this point. But if we believe Fama French 5-factor model, maybe we want to drop somewhere over here and then delete this one. Then what we can do instead is basically we keep PC3 and then PC4, PC5. Okay, then this is our new data set. And then let's check the tail. Tail for the principal component. So yeah. And then for stock analysis, we can keep those 5 factors. Okay, and then we can regard each principal component as a portfolio to make investment. Okay, or to manage our assets, because 821 stocks are like simply too many to administer. So we do principal component analysis and reduce to 5, and we can simply just manage 5 portfolio. That's one idea. And then for stock picking, well, maybe you can develop investment strategy for each PCA, principal component, or you can analyze each 821 stock, and then you can analyze how they are related to each other, right? And then you can find outlier, okay, outlier, okay, to do that. Okay, and then next, Well, next, what I want to do is I want to analyze principal component. I want to analyze what is the characteristics of principal component. So how about, what I can do is I want to analyze, okay, principal component. So for possible investment strategy, let's develop a strategy. In order to develop strategy, I have to analyze principal components. So, well, then to show graph, what I can do is true, and then let's see principal component. Let's see the first principal component plus and PC, the very first principal component, and then uh, and then entire, and then first principal equals to 0. And then let's, yes, so like this one. This is return of the first principal component. Maybe it's hard to, so, well, to see the performance, usually we do cumulative sum. So we add it up. So the performance of first principal component, yeah, like this one. Okay, so, well, clearly we have a big spike at the beginning of COVID-19, big spike. Well, so I can check it is like a negative of market performance, negative general market performance. So the first principal component is like a negative of the general market performance. Line width is 2, 6. So okay, it's slow. Yeah, like this. Huh? How about second principal component? Okay. How about second principal component? Let's look at the shape of the second principal component. Second principal component is second principal component. Again, another very interesting pattern. How about third principal component? Third principal component is very interesting. It is very stable. So if we take negative of this one, then I think it is like a nice portfolio performance, right? I'm not sure whether put just negative works over there, but so yes, if we put minus position of this one, then it has like reasonable pattern. So this is like graphical analysis of the principal component to find the investment implication for each principal component. And then let's do more rigorous analysis. We can do portfolio analytics by regressing by the regression analysis for each principal component. So we will regress each principal component to the famous Fama-Frenchy three factors. Okay, and then what we can do is OLS. We will do OLS, and then first endogenous is the first principal component. So PC, let's say now let's use name this time PC1, and then uh, exogenous is like add as I think add constant. Yeah, add constant, and then we import pharma friendly three factors, pharma friendly three factors, FF3 D, and then everything, and from we will remove the last one because it's risk free rate. They are not pharma friendly three factors, and we will this one. Okay, regression is done. Okay, and then we feed it. So actually, let's use 19. So fit this one. Okay, and then to look at the summary of result. Okay, summary of result looks like this. And then this is not so pretty, so let's put print over here, print over here. Okay, now it looks much better. So as I expected, the first principal component has a large loading to the market portfolio. So it is like roughly in line with the market portfolio, but it also has like a lot of minus loading for SMB. So a lot of loading for large form. So and then a lot of loading for value form. So the first principal component is like a portfolio, mainly in line with big form, and then value form, and like a negative of the market performance in some sense. So if we put minus in front of it, then well, if we put minus, then it is like a market similar to market portfolio, more skewed to small form and then growth form. How about second principal component? The second principal component is, if we look at the results, second principal component is again very interesting. It is like a negatively correlated market. Again, it's a negatively correlated market, but it has big form. It is composed of big form, and it is a big growth form. High is like a big, actually big value form, large value, large traditional forms. Okay, large value forms. How about third one? Okay, how about third one? How about third principal component, which is the most interesting, stable performance. Third principal component, we wanna put, actually, I want to put negative over here, okay? And then third principal component is basically a move against the market, and it has a large loading for small form, and then large loading for growth form. Okay, then it seems that it can generate desirable performance over here. Okay, if we don't have negative, then right, it tends to move with market portfolio, but large form bias, and then growth form bias. So we have to do negative of this to make money. So we have to reduce position in the market, but we have to increase position in big firm. So negative again, put negative over here. So because what I'm doing is because this performance is good. Third principal component, euros good. So yeah, right. Hmm. Because this third principal component is looks nice, and the negative looks nice. So I'm thinking about how to implement what is the characteristics of portfolio and how to implement this portfolio, right? This performance is especially good during the corona pandemic. So to make a good performance during the corona pandemic, we have to go negative against the market, which is natural, and then focus on small firm and then growth firm. As you know, during the COVID-19 pandemic, technology firms, which are usually growth firm, they performed very well, right? Like a Google, Amazon, Facebook, they actually their stock price rose a lot during the pandemic. So it is roughly in line with our intuition. To make money, we have to go against the value form and go against the value form and go to the growth form, small growth form. Okay, that is basic idea. Okay, how about so you can keep continuing this analysis for further principal component. Okay.